All right, lesson 7.2. For those of you that weren't in class today and you feel like you need a little assistance, then you can use this video to help you. If you feel like you know logarithms or you go along the lesson and you're like, oh, I don't need this help, I can do it on my own, then please, by all means, do it on your own and check your answers with the posted answer key in our Google folder. All right, so today, or this lesson, is mainly introducing logarithms. So far you've studied exponentials. And you should have seen something like 2 to some power is going to give you some value, right? 2 to what power will give us 8? Well, when you put in the 3 for x, you get 8 as a result. So your input value is your 3, and your output value is your 8. Logarithms are the inverse of our exponentials. And so this time, you still have the same base. 2 is our base over here, 2 is our base over here. Except this time your input value is 8 and your output value is 3. So log base 2 of 8 will give us 3. So your answer, it's like 2 to the power of 3 will give us 8. So exponential form versus logarithmic form, those are inverses of each other, which will be emphasized a little bit later. But here, if I had rewritten this log base 2 of 8 equals 3, what I like to do is change whatever my base is. If this is a 2, then I'm going to try to change this number here, 8, to a base of 2. So I get 2 to the power of 3. If these two bases are the same, the base of the log and the base of the exponent are the same, then your answer is just going to be 3, because 2 to the power of 3 equals 3. So here, if I look at my examples down here, I have a base of 2. So in other words, it's saying 2 to the power of what will give me 16. So 2 to the power of 4, you might say right away, hopefully. So your answer is 4. Or I could rewrite 16 as 2 to the power of 4. Because my 2's match, oops, my answer is just 4. Right? So 2 to the power of 4, so my answer is 4. And the next one, if I have log base 8, well, this also has a 1/8. 1/8 can be rewritten as 8 to the negative 1. So if I rewrote this as 8 to the negative 1, then my answer would be negative 1. If I have no number here for my base, that means my invisible number is 10. So 10 to what power will give me 100? Well, that answer is 2. Letter D, 3 to what power will give me 1? Well, the only time you can get 1 is if you take something to the power of 0. So 3 to the power of 0 equals 1. Okay, why don't you pause here and try the rest of them on your own and see how you do. So you should have gotten 5 for letter E. Hopefully you recognize that letter F is not possible because you can't have a positive base, raise it to some answer and or raise it to some power and get a negative result. It is not possible. You can't have 2 to some power and get a negative when this base is positive. So this is not possible or no solutions. You put 0 with a line through it. And then I will go right below it. So 7 to what power would give us 0? Well, that's also not possible. You can't take a base to an exponent and get 0 as a result. So these last two, G and H, I left blank. So remember my little shortcut up here. If you made the same base, 8 and 8, 10 and 10, 2 and 2, you just get the answer of whatever that exponent is. Well, here my base was 25, right? So I have 5 squared. I have 5 to the first power. So the top number, this is your numerator, right, of 1, and this is your denominator, so your answer is 1/2. So 25 to the 1/2 power will give me 5. So the square root of 25, that's what 1/2 means, is 5. So here I can rewrite 8 as 2 to the third. I can rewrite 1/2 as 2 to the negative 1. So what is my answer? You should have gotten -1 over 3. So this exponent is the numerator, and this exponent is the denominator. All right, moving on. So here is your form from exponential form into logarithmic form, right? So we have here, if you have a logarithm, log base b, y equals log base b of x, if and only if x equals b to the y power. This only works if the numbers x and b are positive, and of course your base cannot be 1, because 1 to any power is going to be 1, so you'd be in the cyclical unknown, the answer always being 1, so how could you know what power you were taking 1 to? So the numbers x and b always have to be positive, and b cannot equal 1. So here is your logarithmic form, here is your exponential form, log base 2 of x equals 5, or 2 to the 5th power, if and only if 2 to the 5th power equals x. So notice we call this base 2, we call this base 2. You can see how one form translates into the other. What about graphing? Well, when you graph, logs and exponents are inverses of each other, like subtraction is the inverse of addition, or squaring is the inverse of square rooting. Logarithms are the inverse of exponentials. And when you are graphing the inverse, well, let's just figure out here what's going to happen. So inverse, means that we are going to change our ordered pair of x, y, and then when we're taking the inverse, we switch the ordered pairs. So the inverse for logs and exponentials is you just switch the ordered pairs graphically. Okay, so we're talking about it graphically. We just switch the ordered pairs. So here, 2 to the negative 2 power is 1/4, 2 to the negative 1 power is 1/2, 2 to the 0 power is 1, 2 to the 1 power is 2, 2 to the 2 power is 4. So if I graph that, go ahead and graph it. We go negative 2, 1/4, 1/2, 1, 2, and 4. So here is my graph of y equals 2 to the x. Where is my asymptote? So I have a horizontal asymptote at y equals 0. Okay, now, since we just talked about the fact that the log is going to be the inverse of the exponential, and what do? I just switch the ordered pairs. Then when x is 1/4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. So I graph those ordered pairs. And this time, instead of having a horizontal asymptote, I have a vertical asymptote at x equals 0. So notice what happens here. My y's and my x's switch, same here. But what you might also recognize is that your inverses here are the same as a reflection over the y equals x line. So I'm switching my x's and y's. If you were to fold your paper on top of this diagonal line y equals x, then the purple graph and the blue graph should lie right on top of each other, and they will overlap. So those are inverses. All right, your common logarithm. If you have a common logarithm, that means you have a base of 10, and we don't write the base of 10, it would just be blank, and that is automatically means it's a base of 10. For your natural logarithm, your base is e, and we don't have to write the base of e, so instead of writing log base e, we just write ln instead, with e, of course, being that number, 2.718, etc. Okay, for example 2. It says, what happens to the shape of the curve as the base of the exponent or the logarithm changes? So notice here, look at this nice color coordination. This is exponential, 10 to the power of x versus e to the power of x versus 2 to the power of x. Remember, e is 2.71, so it's bigger than 2 to the x. So for exponentials, the larger the base, the what? The growth. So if it's curving in here tighter, closer to the y-axis, then that means our growth is faster, right? It's a steeper curve, so it's growing more rapidly. Logarithms, though, you can see, is the opposite. This is base 2, then we have base 2.71, then we have base 10. So the larger the base, what's happening? Hopefully you're seeing that it is the slower the growth. It's flattening out more quickly there. So notice though, in terms of your points on the graph, sorry, let's just go through that really quickly. Your point on the graph here is 0, 1 for your exponentials. And so for your logs, it is switch them 1, 0. So this is where it's rooted to, where your horizontal asymptote there is at x equals 0. Or sorry, your vertical asymptote is at x equals 0. All right, so now we're going to graph our logarithm. So what I like to do in order to graph is I like to relocate my x and y axes. Remember, your y-axis is traditionally your vertical asymptote for a logarithm. But because we have a +3 in here, we are going to move to the y-axis to the left 3 units. So this is now my new y-axis, or my vertical asymptote. And because we have a -2, I'm going to move my x-axis down 2 units. So now I have a new x-axis down here. So right now at -3, -2, this is, I could pretend, is my new origin. So from your origin, a logarithmic function is rooted to 1, 0, right? But if this is my new origin, I'm just going to go to the right one. So that point should be on this graph. Now I have a negative here in front, so that's going to be a reflection over the y, or over the x-axis is a vertical reflection, so that's a reflection going up and down. So typically your logarithmic function would be going up and to the right, except now because of I have my reflection, it needs to be going down and to the right. So with your base of 2, from the origin, I would go up 1 unit and to the right however many the base is. So if it's 2, this would be my next point. However, because it's reflecting over the x-axis, my point is now below because I've reflected over that x-axis. So my graph should be doing something like this. If I want a third point, I go usually 2 units above, and then I take whatever the base is, which is 2, and then I square it. So I would be going 1, 2, and then squaring it would be 4. So it'd be up here traditionally, but now I'm going to reflect it over my x-axis. So my next point would be down below at 1, -4. Now if you're not sure, and you don't trust me on that, then we can check it, right? So let's put in the numbers I have. So I put in, let's say, -2. I have a value for -1, and I have a value for 1. So if I put in -2, sorry, now I can't see my equation anymore. I have negative log base 2 of -2 plus 3 minus 2. So that's negative log base 2 of 1 minus 2. Well, anything 2 to the power of what will give me 1? Well, that's 0. So it's -0 minus 2, just 0 minus 2, which is -2, and that is my point that I have in my graph. If I do the same thing, but I put in a -1, -1 plus 3 is 2, and log base 2 of 2 is 1, and -1 minus 2 is -3. So -1, -3. Yes, I got that right. If I put in, let's see, if I put in a 1, I would get negative log base 2 of 1 plus 3 minus 2. So it's negative log base 2 of 4. Well, log base 2 of 4 is equal to 2, so it's -2 minus 2, which is equal to -4. So yes, I got those 3 points correct. All right, so we're applying our rules we've already learned in other transformations, other graphs, and just applying them here. So where is my asymptote? Remember, this A stands for asymptote. That's at x equals -3. What is my domain? So my domain is now x is greater than -3, and this time my range is all real numbers. Okay, so if you think you have it, go ahead and pause and try letter B on your own. Okay, so did you get the graph that I have over here? So notice I took this equation and I rewrote the inside. I factored out a negative. So now I can see here that I have to move to the right 5 units. So I relocated my y-axis to the right 5 units. I relocated my x-axis up 1 unit. So this right here is my new origin. Typically I would have rooted my graph to the right over here, except with this negative inside, I now have to do a horizontal reflection. So that's a reflection over the y-axis. So I reflected over here because it's an E, right? It's ln base E. I only have this one point, and then I just go ahead and make my graph. Now I did kind of go, if I go up 1 unit, I'm going to go to the right 2.7. I just roughly made a little point there for 2.7 for my own benefit, but it's not necessary. And that would be a rough sketch of the graph. Okay, moving on, we have 2 more graphs, or this time we have the graph, and you have to come up with the equation. So the first thing you want to do is kind of acknowledge where the asymptotes are. So here's my asymptote, that's clear, and then you want to see where the point is that's 1 unit away from that vertical asymptote. If you have an ln up here, we're only going to give you that 1 point that's that distance away, 1 unit away from the vertical asymptote. So from there, right, well, if that's my 1 unit away, then that's where my x-axis is. So I can see that I moved from my origin, and my new origin is here. So what did I do? I moved to the right 1 unit, which is -1. I moved up 3 units, right 1, up 3, and then, so this would be my answer to that equation. So go ahead and pause and try letter B on your own. Okay, sorry, I just noticed my graph and the graph you have in your booklet are different. So I believe after looking in the booklet, you should have gotten y equals -ln x minus 5. So all you had to do was go down 5 units to relocate your graph. I think the point's over here to the right, and then it looks something like this. So it was reflected over the x-axis, because there's your new x-axis. So you should just have y equals -ln x minus 5. Next, we have our transformations. You know how we'd like to bring these transformations, this theme back. So let's go ahead and try to identify what your transformations would be. So it says, here's our function g of x. G of x equals ln of -2x plus 5 plus 3. So we're going to state the transformations in the correct order that map the function f of x equals ln x onto g of x. So the first thing I'd recommend you do is to rewrite that inside by factoring out the -2. So when I factor out my -2, then I can see more clearly, you know, I move to the right 5/2. Otherwise, you might have made that mistake. So step number 1, we have our reflection here, and if it's on the inside, that's a reflection that is horizontal. So we're reflecting over the y-axis because it's a horizontal reflection. The second thing we have to deal with is our 2. So again, it's in here associated with the x, that's horizontal dilation. And remember, when it's associated with the horizontal, it's doing the opposite. So if it's a 2, it's not actually getting twice as wide, it's getting half as wide. So it's a horizontal dilation of 1/2. So I should have said of 1/2. And then our last thing, it doesn't matter the order that you do it, but you could say right 5/2 and up 3. So right 5/2 and up 3. So what is our domain of g of x? Well, if this is my function, what do we want our domain to be? What is never allowed to happen, right? If we have ln of -2x plus 5 plus 3 equals y, well, this inside part right here can never be negative. So we have to make sure that -2x plus 5 is then always positive. So we do this equation, we just solve. So I get negative 2x is greater than negative 5, right? Subtract 5 from both sides. Divide each side by negative 2, but when you divide by a negative, you have to switch the sign. So the domain is such that it's going to be x is less than 5 halves. And that's it. Example 6, we're almost done here. A couple more left. So example 6, it says determine the inverse. So in order to determine the inverse, you have to switch the x and y. And then number 2, solve for your new y. And number 3, replace y with f to the negative 1 of x, because we want you to have that inverse notation. So here's my function. So I'm going to switch x and y. So originally it's y equals 1/3 e to the x plus 4 minus 1. So now it's going to be x equals 1/3 e to the y plus 4 minus 1. So I switch that. I have to add 1 to both sides. So I get x plus 1 equals 1/3 times e to the y plus 4. The next thing I have to do is multiply by 3. So now I get 3 times x plus 1 equals e to the y plus 4. Now my variable is up here as an exponent. So if my variable is an exponent, the only way I can get that variable to no longer be an exponent is to rewrite. This is exponential form. So I need to rewrite my exponential form into logarithmic form. So my base is e. So if my base is e, I'm either going to write log e, or log e is just the same as ln. So that's my base. What it equals is what goes here next to it. And then e to the power of y plus 4, right? So it's e to the power of y plus 4 equals 3 times x plus 1. So if you go back and look at your definition or your rule for exponentials, this is what you will see. So my final step to isolate my y is to subtract 4. So I'm going to get ln 3x plus 1 minus 4 equals my y. And then finally, my last step is to replace my y with my inverse notation. So I'm just going to do that nice and neatly now. So instead of a y there, I'm going to have f to the negative 1 of x to indicate that this is in fact the inverse of my original function. All right, so in our final two questions, you're going to have a big chunk of problems on there where you're going to have to solve algebraically. This is one type of solving problem. So in order to solve algebraically for these two, well, do you notice what can you do? Is there anything that might come kind of stick out to you as maybe a strategy you should use? If you're totally baffled, then I'm going to help you out. Oops. So if we let e to the x equal lowercase a, right? So I'm going to take this, I'm going to say, let's say that's equal to lowercase a. Well, this is e to the 2x. So e to the 2x is the same as e to the x squared, right? Because the rule is that we multiply those exponents to each other. So if that's the same as e to the x squared, then that's the same as a squared. So now wherever you see e to the 2x, we can write a squared, and wherever you see e to the x, you can write a. So we get just a regular old trinomial, and so we can factor this. It's just a quadratic trinomial, so what are we going to do? What two numbers multiply to give me -6, but add to give me -1? So hopefully you're thinking -3 plus 2. And so a equals 3, where a equals -2. But remember, it's not actually a. It's actually e to the x. So it's e to the x equals 3 and e to the x equals -2. Hopefully there's some alarm bells going off in your head going, wait a minute, I can't have a positive base of e, 2.71 blah 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 to the x power, and somehow get a negative number. It's not possible. So we want to see that recognition by you, by either putting a 0 with a line through it, like saying there's no solution for this, or you can cross it off and say that's not possible. You're letting us know that you've thought about it and you realize that's not an answer that's possible. For this one though, we have to isolate x. How can we isolate x? Again, if x is your exponent, then you have to rewrite exponential form into log form. So if we want to isolate x, we're going to say log base e of 3 equals x, or just, ln 3 equals x. So my answer is just ln 3. You don't have a calculator. You don't need a calculator. You just leave it. This is called exact form, right? So it's just ln 3. That's your answer. So looking at this strategy here, apply it over here. It's a trinomial again that you can factor. So pause, try it on your own, and then you can check back. Okay, so did you get the exact same answer? Just coincidentally, the answer was x equals ln 3. When you did the substitution again, you should have had a trinomial you factored. You either got a equals negative 2/3 or a equals 3, or e to the x equals 3 or e to the x equals negative 2/3. You can't have a positive base, somehow get a negative answer, so that crosses off. It's no solution. So my only possibility was x equals ln 3. That's it. That's a lot of information. Hopefully this helped. Contact your teacher if you have any questions. And yeah, take it easy.